All right, let's dive into something really cool today, the world of waves.
Ooh, I like that. Waves, they're everywhere, right?
Absolutely. From the ocean to the music we listen to, even light. It's all about waves. Perfect deep dive material for, say, oh, I don't know, maybe a high school physical science class.
Totally. In this deep dive, we're going to try and cover it all.
We'll see how we do. At least that's what our source material is telling us to shoot for, right? Understanding how waves work, how we use them in technology, the whole 9 yards.
Ambitious, I love it. Let's go.
Okay, so first things first. Our source material lays out some pretty important terms. Frequency, velocity, wavelength, energy. What are these all about?
Well, you got to start with the basics, right? Think of a wave as like a repeating pattern.
Okay, I can see that.
The frequency is just how many times that pattern repeats in a second. Imagine a surfer riding a wave.
Okay, yeah, I'm picturing it.
The distance between the crests of those waves, that's your wavelength, and the faster that surfer is moving, the higher the velocity of the wave is going to be. Makes
Yeah.
sense.
It does. So that means a wave with a shorter wavelength would actually have a higher frequency.
You got it, exactly. And then we've got energy, which is tied to the wave's amplitude, basically how high those crests are.
So a bigger wave carries more energy.
Exactly. Think about a tsunami versus a little ripple in a pond. The tsunami obviously packs way more energy, right?
Definitely. But does the energy always stay the same as a wave travels?
It's a great question. And the answer is not always. Have you ever noticed how, like, a siren sounds louder when it's close to you,
Yeah.
and then it kind of fades as it moves further away? Well, that's because the wave's energy is spreading out over a larger area, following, get this, the inverse square law. It's physics in action.
I never even thought about it that way. That's really cool.
Physics is pretty cool.
So our source material also mentions these things called mechanical waves and electromagnetic waves.
Right.
What's the deal with those? What's the big difference?
All right, well, a mechanical wave is a wave that needs something, a medium to travel through, like water or air. Think about sound waves for a second.
Okay, I am.
You can't hear anything in the vacuum of space, right?
Okay.
And that's because there's no air for those sound waves to, vibrate and travel through.
So if I were to yell in space,
Hmm.
no one could hear me scream.
Sorry, but that's the hard truth. But light waves, on the other hand, those are totally different.
Interesting.
Light waves, those are electromagnetic waves. They can travel through the vacuum of space, which is good news for all of us. That's how we get sunlight from the sun, even though there's nothing but, well, empty space in between.
So light is a wave.
Hmm.
I mean, I kind of knew that, but never really thought about it like that.
Right. It's pretty mind-blowing when you think about it. It's literally how we get to see the world around us, the colors, the shapes, all thanks to light waves.
All right, well, speaking of seeing, that kind of brings us to how waves interact with their surroundings, right?
Hmm.
Our source material talks about reflection, refraction, diffraction, and interference.
Oh, the fun stuff, the cool stuff.
Yeah. So reflection, that's easy enough, right? That's just like when I look in the mirror,
Exactly. The light waves are bouncing back at you. But what about the others?
refraction always sounded kind of cool to me, not gonna lie.
Oh, refraction is awesome. It's when a wave changes direction as it passes from one medium to another. Like, picture this. You put a pencil in a glass of water,
Okay, I got it.
and it looks bent, right? Like broken almost.
Yeah.
That's because those light waves are bending as they pass from the water into the air. It's like they're taking a detour.
I always thought that was so weird as a kid.
Right. It messes with your brain.
Okay, so what about diffraction? Is that like those noise barriers you see
Yeah.
along the highway?
Yes, you got it. Diffraction is when waves like bend around obstacles or like squeeze through openings.
Yeah.
And yeah, those barriers are designed to, diffract those sound waves and reduce noise pollution. So,
So smart, right?
pretty clever.
Hmm.
All right, last one. Interference. It's hard to imagine waves actually canceling each other out.
It seems counterintuitive, but it happens all the time. Think about noise-canceling headphones.
Oh, yeah, good point. They're creating sound waves that are out of phase with the unwanted noise, the annoying sounds, and that leads to something called destructive interference. So basically, the waves cancel each other out and boom, silence.
So is it kind of like, I don't know, adding a positive number and a negative number?
Exactly. You're on fire today. They just cancel out, to zero.
It's a perfect analogy.
It is. And just like with numbers, when waves are in phase, well, they amplify each other. It's called constructive interference. And you can see this when, two sets of ripples in a pond overlap. They create these even larger waves where they meet.
So we've got all these, like, awesome wave interactions happening all around us all the time.
Hmm.
What does our source material say about how we actually like use this stuff in technology? Because I know we do. We use waves for a ton of things.
Oh, we do. Our source talks about instruments that utilize these phenomena, and it's quite the list. Like, take ultrasound, for example.
Like ultrasounds.
Doctors use ultrasound to create images inside the body. It uses sound waves and their reflections. And because of that, doctors can see what's going on without having to do surgery.
Amazing, right?
It's incredible.
It is. And then we've got radio telescopes. Have you heard of those?
Of course.
Well, they're detecting radio waves from space, which are just another type of electromagnetic wave.
Exactly.
And by studying those waves, we can learn so much about distant galaxies and even the origins of the universe.
Wild. And even just like a regular fiber optic cable, I mean, that uses total internal reflection of light waves, right? To transmit information really fast.
Yeah. It's basically bouncing light off the walls of these tiny glass fibers. And that's how we get super fast internet and, all the cool stuff that comes with it.
It's amazing. We've taken these basic principles of waves and we've figured out how to use them to create all of this technology.
Yeah.
It's wild to think about how much of our modern world depends on these things. Right. It's in everything. And it just begs the question, if we can manipulate waves in so many ways, what else is out there,
Yeah.
What other incredible technologies are waiting to be discovered? What problems could we solve? Who knows? Maybe some of our high school listeners out there will be the ones to figure it out.
Now, that's an awesome thought to leave everyone with. This deep dive has been incredible. From surfers to space telescopes, I mean, it's clear waves are everywhere. And understanding them is a key to unlocking a whole world of possibilities.
It really is.
So until next time, keep riding those waves of knowledge, everyone.
Catch you later.